Hello everyone. So in this video, I'm going to walk through example 7.5 from Atkins and Friedman, page 243 and 244, and homework 1B from problem set 10. Okay. And so our goal here is to construct the term symbols when we're given the configuration, right? So in example 7.5, we're given 2p1, 3p1. And the textbook gives you the answer, and it also gives you sort of a brief walkthrough on how to obtain this answer. Okay, and so I will walk through it and hopefully it'll make more sense on how I got my answer for 1B. So for example 7.5, when I look at this, I see that 2p1 and 3p1 are unfilled, right? Because p1 and p1, right, they can be filled more, right? It's a p orbital. So the max that it can hold, right, p orbitals, they can hold up to 6 electrons, right? Right, so just remember that, right? So these are unfilled, and so I know that I'm going to have to use both of them, right? So we know that. That's basic, right? When I look at this, my brain thinks, all right, if I'm going to construct a term symbol, there are things I'm going to need. If you recall, the term symbol is 2s plus 1, L sub j. And in order to construct a term symbol, you need 3 things. You need S, you need big L, and you need big J. And so the question is, how do I go about doing that? And so my brain says, all right, well, we know we are dealing with a 2p1 and a 3p1. And I recall that L corresponds with certain letters, right? The numerical values of L corresponds with different letters. So L, right, 0, 1, 2, 3, 4, it corresponds with S, P, D, F, G, etc., and so forth, right? And so my brain tells me then, okay, if I look at this P refers to L1, that value then is 1. So L1 is equal to 1. My brain then looks at 3p1 and it tells me that P, right, corresponds with 1 as well. But we'll call this L is equal to 2, right? And so here I can write it in this way. So L2 is equal to 1 if that works for you, right? Looks nicer. So we know L1 is equal to 1 and L2 is equal to 1. And this is verified by the textbook. The textbook says, hey, for this configuration, L1 is equal to 1 and L2 is equal to 1. So big L, right? Big L is equal to what? Right? This is what we're trying to find. So what is big L? Well, big L, right, is then going to be 2, 1, and 0. How did I get that? Well, you can refer back to what it means to be L in terms of like the equation. So we'll go back and I looked at a source called ChemLibre, and we can see here that L is equal to, here, let me pull up annotations. L is equal to the absolute magnitude of L1 plus L2, comma, absolute magnitude of L1 plus L2 minus 1, comma, dot, 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 all the way down to L1. I mean, I didn't need to write this, but I mean, I just want to write it. So this is big L, all right? And that's what we want in our term symbol, right? 2s plus 1j. Honestly, I forget the names of what these are. So L, big L, refers to the total orbital angular momentum quantum. I mean, you could read for yourself, but that is what big L is. That's what it's called. I just forget it, which is not good. But if you want to refer to this, this is what the name of the ChemLibre is. Term symbols. I mean, you can also read this too. You can search it up. But one thing to note is that big L can never be negative, right? So, I mean, that's nice to know that it's the absolute magnitude between L1 plus L2, etc. And in between are integer steps, right? If I click my annotations, this is your max and this is your min, right? So let me go ahead and clear my annotations and let's go back to OneNote. And so we can see that L big L is equal to 2, 1, 0. What do these correspond with? Well, big L also corresponds with, which is very similar, right, to these letters, S, P, D, F. These are capitals, right? So 2 corresponds with D, 1 corresponds with 2, and 0 corresponds with S. Oh, 1 corresponds with P. I don't know why I said 2. Sorry about that. So D, P, and S. Oh, we're 1/3 of the way. We need to find the spin number. Let me refer back to that. This is the spin number right here. Spin number, because the spin number will give us the spin multiplicity. So how do we go about doing that? So my brain thinks about this and it says, okay, well, if you want to find big S, right, this the spin number, right, what do you need to do? Well, you need to think about, what does it mean to be a spin number? Well, it comes from the electrons, right? If you think about electrons, right, in the 2p1 and 3p1, we know we have 2 electrons, and we know that 2 electrons, what's so special about them? 1 electron can be up, 1 electron can be down, right? 1 electron can be up, the other electron can also be up. 1 electron can be down, and the other electron can also be down, right? So if I were to, use the numerical, representation of up and down, right? Up is +1/2, down is -1/2, right? I should space these out. +1/2, right? -1/2. These aren't multiplying. I'm just writing them in parentheses. +1/2, +1/2, and -1/2, -1/2, right? Because that's down, down, right? And so S, right, is called the spin number. And how do I get them? Well, they come from little s1 plus s2, comma, s1 plus s2 minus 1, comma, dot, 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 s1 minus s2. And I believe that these are actually should be magnitudes. So there's absolute values around them. So big S, the spin number, should always be positive, right? And so if we plug in S1, right, let's say S1 was equal to +1/2, S2 is equal to +1/2, right? Then what you get then is 1, comma, and then if you do the very minimal, right, S1 minus, this is not a comma, this is a 1, sorry. S1 minus S2, you get 0. So just big S is equal to 1, 0. What if they were both down? Well, if it was S1 is -1/2, if this were the case, right, -1/2, -1/2, you would still get S is equal to 1 and 0 as the result. Right? If 1 was plus, you'd still get S is equal to 1 and 0, right? Okay, so we know that big S is equal to 1 or 0. All right, and so this is perfect. So what does that tell me then? Let me go ahead and let me show you what that means for us. So we found very good things. Big L can be 2, 1, 0. Big S can be 1 and 0. Sorry, I'm hesitating. I get scared. But what does that mean for us? We can go ahead and we can construct our term symbols now. Why did I do that? 2s plus 1, L, and J. We know L, we know S, and we know J. J is actually just L plus S, all the way down to L plus S minus 1, comma, dot, dot, dot. Let me make space. L plus X. This is L minus 1. My bad. So that's L minus 1. And if you go back to the source here, right, Chem Libre as a reference, S is equal to S1 plus S2, S1 plus S2 minus 1, dot, 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 all the way down. And if you look at J, J is equal to L plus S, all the way down to L minus S. So we are now at a position to construct our term symbols. So if I said L is equal to 2, it could be 1 or 0. So L is equal to 2 could be S is equal to 1, S is equal to 0. If I was L is equal to 1, so this is sort of like a combinations thing. You just got to combine it. S can be 1, S can be 0. If L is equal to 0, S can be 1, S can be 0, right? And so what comes out of this then is 2 times 1 plus 1 L, which we said was if it's 2, right, then it's going to correspond with D, right? We set it up here. Let me show you right here. So if L is equal to 2, it corresponds with D. If L is equal to 1, it corresponds with P. If L is equal to 0, it corresponds with S. All right. So 2 plus 1, I mean 2 times 1 plus 1 is essentially 3. I'm not going to show the work now. So it's 3D. And what is J? Well, we know J is equal to L plus S, right? So that's 2 plus 1, comma, dot, 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 all the way to 2 minus S, 1. So that's 3, comma, dot, 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 all the way down to 1. That's the lowest, right? But it needs to go in integer steps. So integer means like just 1, so plus 1 or minus 1, right? Minus 1. That leads to 2, and to 2 to 1 is minus 1. So those are integer steps. So the possible J values then is 3, 2, 1. So technically, what happens here is you have 3D, 3. Let me write it better. 3D3, 3D2, and 3D1, right? What about this one right here? So I'm going to go through the same process and hopefully it'll make more sense. We know that L is equal to 2, so this corresponds with big D, but we know that in this case, S is equal to 0, big S. So if you did the spin multiplicity, 2 times 0 plus 1 is equal to 1, so that's 1 here in the upper left hand. And if I were to do J, J is equal to L plus S, comma, dot, 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 all the way down to L minus S. So that's L plus S, that's 2 plus 0, that's 2, comma, dot, dot, dot. What's 2 minus 0? That's 2. So that's only 2. So J is equal to 2. So 1D2 is one of them. 1D2. All right. So that's 1D2. All right. And you repeat the same process for each one. Right. So if L is equal to 1, S is equal to 1, that is 3. And we said, what does L is equal to 1 corresponds with? That corresponds with P. So that's 3P. In J, what is J, right? I always have to think about this. L plus S, comma, dot, 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 all the way down to L minus S. This is equal to 1 plus 1, all the way down, dot, 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 to 0, because that's 1 minus 1. 2, comma, dot, 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 all the way down to 0. Now you need to include the integer multiples or the integer steps. So this is 2, 1, 0. So you result in 3p2, 3p1, 3p0, right? Now we repeat the same process. L is equal to 0, S is equal to 1. When L is equal to 0, that corresponds with S. When S is equal to 1, that corresponds to 3, right? And so when we consider J, J is essentially L plus S, comma, dot, 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 L minus S, right? We said L is equal to 0, S is equal to 1, so 0 plus 1 is essentially 1, comma, dot, dot, dot. What is L? 0. 0 minus 1 is negative 1. The absolute magnitude of negative 1 is 1, or the absolute value, I mean. So that's just 1. So 3s1, right? And then the next one is S. S is equal to 0. L is equal to 0. So we know that this is 1 up here, and J is equal to 0. So that's 0 in the bottom right hand. And what you find here is you've just found all the term symbols. And what's really nice is you never had to use a microstate table. But I'll go ahead and at the end of this video, I'll explain why a microstate, I mean, I'm not going to explain why. I'll explain it right now. In some configurations, right, you'll find that using this method, you're forgetting about something. I know I'm being a little wavy here, but essentially, microstate tables, when I'm just going to show you a microstate table. How about that? So a p set 10, right, 1b, I constructed a microstate table to get all my possibilities, right? And what I can say about microstate tables is, you don't have to do it all the time, but it's a foolproof method. It's a very tedious one, but once you have it down, it's not bad. It's just a long process, right? And it works 100% of the time, right? The method that we did here, where we just wrote this out, you have to be careful. There are going to be cases where you didn't think about something and it's just not going to give you the right term symbols. So I like to use the microstate table method because I just don't like to think about what could go wrong. I just, work on I guess the longer process. But this is the answer that you get, right? For the example from the textbook. And this is how you do it, right? And this matches up perfectly with what the textbook got as well. Now, one thing I will add is how can you check your work? What's a good way of checking your work? So what's nice is that from each term symbol, you can find out how many microstates arises using the equation 2j plus 1. So if that's 3, right? If j is equal to 3, 3 times 2 plus 1 is 7. So there's 7 microstates here. And I repeat the same process. I look at this term and I say, all right, 2 times 2 plus 1, right? This is, why am I blanking? 4 plus 1. This is 5 microstates. I don't know why. That was a little weird. 3d1, right, is, I always have to write this out. 2 times 1 plus 1. That is 3 microstates, all right? So you just continue the process, right? So d2, right, 2 times 2 is 4, 4 plus 1 is 5. 2, well, I know that's 5. I know this is 3. 0 times 2 plus 1 is just 1. I just really want to make sure I'm doing this right for you. 1 times 2 plus 1, all right, 1 times 2 is 2. 2 plus 1 is 3. 0 times 2 is 0. 0 plus 1 is 1. All right. So if you were to add these all up, 7 plus 5 is 12. 3 plus 5 is 8. 12 plus 8 is 20. That's 25. 25 plus 3 is 28. 21 plus, 1 plus 28 is 29. 29 plus 3 is 32. 32 plus, 33. Oh, I made a mistake somewhere. And I know this. How do I know that I've made a mistake somewhere? I don't, it's not fun. Where did I make a mistake? I made a mistake somewhere. Oh, okay, well, I'll tell you how I knew I made a mistake. Well, I made a mistake because, well, just first off, okay, I made a mistake because I can use this, right, to count the number of microstates I should have in the end. So n is the number of states an electron can be in. So if you consider the p orbitals, right, there's 6 possible states. I can be here, up, down, down, or up, right? So that's 1. Up here, that's 2. Up here, that's 3, right? Or I can be down, that's 4. Or I can be down here, that's 5. Or I can be down here, that's 6. So 6 states, so n is equal to 6. So 6 over the amount of electrons, and we're only dealing with 1, right? It's 2p1 here, 2p1. So that's 1 electron. So 6 factorial, 1 factorial, 6 minus 1 factorial times, you also need to consider 3p1, 6 factorial, because it's also a p orbital, 1 factorial times 6 minus 1 factorial, right? And I multiply them because this is 2p1, this is 3p1, right? And we said that in a p orbital, there's 6 possible states you can be in. So this is then equal to 6 factorial, 5 factorial, times 6 factorial over 5 factorial, right? That's essentially just 6 times 6, right? because 6 times 5 times 4 times 3 times 2 times 1 all over 5 times 4 times 3 times 2 times 1. You can cancel the tops and you're left with 6, right? So that's 6 times 6 is equal to 36. I counted 33, so I can tell I messed up somewhere. I think I messed up with one of the multiplications. Or I did not list out all the states, which I'm pretty sure I did list out all of them. 3D3, 3D2, 3D1, 1D2, 3P2, 3P1, 3P0. Uh-oh. This is where I found my mistake. So L is equal to 1, S is equal to 0. So that refers to P, 0, 1, 1, P, and this is going to be L plus S. This is 1. All right, and if that is 1, that contributes 3 states. So I found my extra 3 here. So that's 36. Okay, sorry to the audience who's watching this right now. So that's 36. So I'm good. I've effectively, verified that, hey, I ended up with the correct amount of states at the end, right? So that's great. Another way you could also do this, well, I won't go into that, but this is for the textbook, how to do the textbook. Now we move on to the homework problem, 1B. So 1B, right? Sorry, my handwriting's getting really messy, but 1B was 3P1, 3D1. 1B was 3P1, 3D1. So again, I'm not sure if I told you this, if I said this in the, if I said this in this video, but essentially, you notice how here we're not using any microstate tables. And again, I think I said it, but microstate tables are the foolproof method. It's long, it's tiring, and it might not be really good for exams because you have to write out so much. But I'd say just use the microstate table as a way to figure out how things are being constructed. This method, I say, with the method we're using here without using any microstate tables, it only works for some of them. I mean, I don't know if that's true, but I don't know. In my cases, I would stick with microstate tables, and I'll get back to other people if there's another okay. The reason why I'm, thinking that this method doesn't hold true for all of them is because if this entire method, we could use for every single configuration, then there would be no need, right? There wouldn't be a need for any of this. If we could just do it simply by the other method, right? We wouldn't need to construct tables. But I don't know. I guess what I'm saying here is I would just be careful using this method 100% of the time. And that is why I've elected to practice the microstate table, because this method may not be reliable. But I will find out what are the conditions to use this method, if this makes any sense at all. But okay, let's go ahead and get started with 1B. I've talked too much. So 3P1, 3D1. What does my brain think? All right, so how do I get started? Well, let's go ahead and start with verification. How many microstates should you end up with? We know from the equation that the number of microstates you should end up with, right, is equal to n factorial over e factorial and minus 1. No. Yes. No, wait, hold on. N minus e factorial. Yes. N minus e factorial. So this is equal to, right, when we were doing this with 3p1, 3d1, 3p1 times 3d1, right? Yes. So if we look at 3p1, right, p orbitals, there's 3, and the electron can exhibit 6 possible states. So it can be up here, up here, up here, right? So that's 3 possible states, or it can be down, down, down. That's another 3, so that's 6. If you do a d orbital, that's 1, 2, 3, 4, 5. It can be all up, which is 5 states up, 5 states down, right? Or 5 possibilities down. I shouldn't say states, but I should say possibilities. Sorry for that. That is then going to be 6 factorial all over how many electrons? There's just one, right? There's just one electron. So that's 1 factorial, 6 minus 1 factorial, and this is multiplied by 10 factorial, 1 factorial, 10 minus 1 factorial. And so this is going to be 6 over 5 factorial times 10 factorial over 9 factorial, which is essentially just equal to 6 times 10 is equal to 60. And this is because, again, remember 6 times 5 times 4 times 3 times 2 times 1 all over 5 times 4 times 3 times 2 times 1 cancels out, right? And so you're left with 6 on the numerator. And that same idea applies to 10 factorial over 9 factorial. I'm going a little fast just because I made this video so long and I feel bad. So this is 60 microstates that you should end up with, right? So let's go ahead and let's start with how I think. So 3p1, 3d1, I tell myself and I say, hey, I know p corresponds with an L value of 1. So I can say L1 is equal to 1. And d corresponds with an L value of L2 is equal to 2. I just call this L2. And you could do this the other way. You could say that this is L2 is equal to 1. And you can say L2 is equal to 2. I mean, L1 is equal to 2. Oh my God, I'm messing up. So that's L1 is equal to 2, right? But, I like to start from left and right. L1 is equal to 1. L2 is equal to 2. And how did I know this? I looked at the letters P and D, and I said to myself, well, if you recall, that P and D correspond with 1 and 2 respectively, right? So L is equal to 1, L is equal to 2. Yes, L1 is equal to 1, L2 is equal to 2. And L, big L, is equal to the absolute magnitude of L1 plus L2, absolute magnitude, comma, dot, 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 sorry, I just got a text message and I'm looking at it right now. I shouldn't be doing that. That's L1 minus L2. All right, so this is equal to 3, 2, 1. All right, oh, okay, I'll show my work. So this is equal to L1 plus L2, right, is 1 plus 2, comma, dot, 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 all the way down to 1 minus 2, which is negative 1. Negative 1, absolute magnitude is just 1. This is just 3. But you need that integer step, so that's 2. So L is equal to 3, 2, 1. So these correspond with P, D, and F, right? Oh, yay, you got your L value. What about your S value? Well, it turns out that you're dealing with 2 electrons. And so S is equal to 1 and 0. And again, how did I get that? So this is what big S is. This is the spin number, 1 and 0. How did I get that? Well, again, if you recall, electrons can be up, down. When we're talking about two electrons, right? One of them can be up, one of them can be down. One of them can be up, one of them can be up. One of them can be down, one of them can also be down. So in this case, you have plus 1/2, negative 1/2, plus 1/2, plus 1/2, right? This is negative 1/2, negative 1/2. And the equation for big S spin number tells you, well, S1 plus S2, right, the absolute magnitude, comma, dot, 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 should go all the way down in integer steps to S1 minus S2. So you can designate this as S1, you can designate this as S2, and what you get here is you get 0, right? So 0 is equal to 0, comma, dot, 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 all the way to S1 minus S2. So S1 is 1/2 minus S2, right? Right, that's 1. So that's 1 to 0. So big S is equal to 0 or 1. And you can do the same thing. You can instead say, hey, I want to use this as S1 and this is S2. So you can say, all right, plus 1/2 plus the positive 1/2, right? comma, dot, 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 all the way to 1/2. I'm just going to leave out the positives, right? Is 1 all the way to 0, right? So big S, in the end game, right? S is 1 or 0, 1 comma 0, right? Spin number, right? So that's how I got it. I hope that makes sense. If it doesn't, try to reach out to me. So S is equal to 1 and 0. Right. So we're at a good place, right? So L is equal to 3. L is equal to 2. I'm going to do a little different formatting right now. L is equal to 1. Hold on, let me erase this wall because it looks so sloppy. L is equal to 3. L is equal, that still looks sloppy. L is equal to 2. L is equal to 1, right? S can be equal to 1. S can equal to 1. I'm running out of air. S is equal to 1. L is equal to 3. S is equal to 0. L is equal to 2. S is equal to 0. L is equal to 2. Nope. L is equal to 1. And S is equal to 0. How did I do this combination? So I looked at L is equal to 3, 2, or 1. It's like combinations, right? And if your possible S values, right, S can be either 1 or 0, 1 or 0, 1 or 0, right? So that's just, combining them up. And so from there, what I can then do is I can calculate my J values. So if you recall, J is equal to L plus S, right? Comma, dot, 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 all the way to L minus S. And these are absolute magnitudes again. So they can never be negative, right? Yes. I'm a little iffy on that. Yes, yes, they can. L plus, if I annotate right here, that one. L plus S all the way to the absolute magnitude. So I guess it's always going to be positive, right? Most values will always be positive. Clear all the notations. Sorry, oh, I ran overtime so bad. So J is equal to 4 all the way down to 2. So it's 4, 3, 2. I did it. This J is equal to 3. 2 plus 1 is 3. 2 minus 1 is 1. So it's 3 all the way down to 1, but in integer steps. So 3, 2, 1. J is equal to 1 plus 1, which is 2, all the way down to 0, because 1 minus 1 is 0. So you need to go integer steps. That's 1 and 0. J is equal to, so I'll do this one, L plus S, comma, all the way down to L minus S. So that's 3 plus 0, comma, dot, 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 all the way to 3 minus 0, the positive magnitude or the absolute value. So that's just 3, right? L. So it's just the end result is just 3. J is equal to 3. L is equal to, nope, J is equal to 2, and J is equal to 1. And you can construct your term symbols now. So if you look at this one, right, what are you? Your L is equal to 3. So if I recall that this corresponds with, I always have to do this, S, P, D, F. So it corresponds with F. So I will write it in red. So this is F, right? And S is 1. So that means that the spin multiplicity, 1 times 2 plus, so 2S plus 1, right? If S is 1, that means that it's going to equal to 3. So 3F4, 3F3, 3F2, comma, we'll do this one next. L is equal to 3, so that's F. S is equal to 0, so that's 1. J is equal to 3, so 1F3. And we'll do the next one. We'll do this in blue. We'll use these two in blue. So these become L is equal to 2, right? That corresponds with D. S is equal to 1. That corresponds with 3 for the spin multiplicity, because 2 times 1 plus 1 is 3, right? I'll repeat that. So I know I'm going a little fast. I just don't want this video to be so long and then it won't upload in time to share with you all. So 2S plus 1, right? That's the spin multiplicity. S is equal to 1. That's going to be 1 times 2 plus 3. 1 times 2 plus 1 is equal to 3. That's going to be 3F, 3F3, 3F2, and I'm getting them from the J values. 3F1, comma, comma. And then I look at L is equal to 2, S is equal to 0, J is equal to 2. All right, so as L is equal to 2, if L is equal to 2, that's F. S is equal to 0, that's the spin multiplicity of 1. J is equal to 2. So this is what you should be getting, right? I hope this is what you're getting. Uh-oh. 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 I made a mistake. I was going so fast. See, I made a big mistake. I'm so sorry about that. L is equal to 2. That corresponds with D. You must like 10 seconds ago must have been like, what is he doing? So this is 3D, D, 3D2, 3D1. And what's the next one? This is D, this is 1, and this is 2, right? I feel so bad for making that mistake. That was going too fast. So L is equal to 1, L is equal to 1, right? So let's go slower. So we know L is equal to 1 corresponds with P. So this is P. And we know that if S is equal to 1, the spin multiplicity 2S plus 1 is equal to 3 when S is equal to 1, right? So this is 3. And the J values are 2. Why isn't it erasing? I'm panicking. 2, 3p2, 3p1, and 3p0. If we look at this one, right here, this one, then P, right, L is equal to 1, S is equal to 0, so that's 1, and J is equal to 1. So these are all our term symbols. And what you will find then is that they will add up to 60. So if you look at 3f4, right, 4 times 2, to do the states, you do 2j plus 1 for each term symbol, right? And this is the number of microstates for each term symbol, right? So how do you do that? That's 2 times 4 plus 1, 2 times 3 plus 1, 2 times 2 plus 1, 2 times 3 plus 1. What you get is 5, 7, 9, and you get 7 here. And so this totals to be, I can't do math. 12 plus 7 is 19. 19 plus 9 is 28. Blue is 2 times 3 plus 1, 2 times 2 plus 1, 2 times 1 plus 1, 2 times 2 plus 1. And recall the equation is 2j plus 1 to get your states, the number of microstates, right? So I'm simply just looking at the j values and plugging them in. So this is equal to, so this is just proving or, double checking that I did this right. 2 times 3 is 6, so that's 7. 2 times 2 is 4, so that's 5. 2 times 1 is 2, so that's 3. That's 5. So that is 10 plus 10 is 20. And then the green, right? So we do 2 times 2 plus 1, 2 times 1 plus 1, 2 times 0 plus 1, and 2 times 1 plus 1. So you get 5, you get 3, you get 1, and you get 3. So this is, what is that equal to? 6 plus 3, right, is, no, 6 plus 1, that's 12. That's 12. And if you check, right, you get 32, right, or here, I'll combine them. This is 32 together, right, plus the 28 from here. So that's equal to 60. Woohoo! You've proved that there are 60 microstates total from earlier, right? So, these are the correct term. This is most likely, this increases the chance that you probably did your term symbols correctly. Now, look how we never even touched a microstate table. Now, that's really nice. I would say, like, definitely use this method on a test, use it on your homework. But I like staying with a microstate table just because, I'm a little scared that I might do something wrong. And even then, when constructing a microstate table like this, you could still do something wrong. So here you can see I have 60 total. and I've condensed it down into a table. And after I'm, shrinking down each table, I'm getting the term values or the term symbols: 3F4, 3F3, 3F2, 1F3, 3D, 3D, 3, all these, right? And it matches with what we got here in, what do you call it? Um, in this part right here. Uh, these answers correspond with, um, oh, no, went too far. Correspond with what we got here as well, using microstate tables. But you can see that it took me 3 pages just to do a microstate table. And just imagine on a test, on a final, how long it would take. So absolutely, go ahead and I would say use the method, but there are some limitations of this method, because otherwise, if this method were to hold true, we would always use it. We would never even touch microstate tables. So I would say, be careful, and I'm going to try and find out when we can't use this method, because this is such a nice method. It cuts down the work time really quickly. I mean, yeah, really, I guess really small. But yes, I hope this video was helpful, and I will stop the video. Oh my God, am I recording? Okay, yes, I am. Okay. Oh, goodbye.